cyclic heat engine does 50 kilojoules of work per cycle. If the efficiency of heat engine is 75%, the heat rejected per cycle is A. 16 2 by 3 kilojoules, B. 33 1 by 3 kilojoules, C. 37.5 kilojoules, D. 66 2 by 3 kilojoules. The solution to this problem could be given as, let us represent the problem pictorially. A cyclic heat engine is producing work output of 50 kilojoules, where Qs is heat supplied, Qr is the heat rejected. Thermal efficiency of any heat engine cycle is given as W divided by Qs, which is given as 0.75 in the problem, implies 50 divided by Qs is equal to 0.75, which is equal to 3 by 4. Therefore, Qs is equal to 4 into 50 by 3 kilojoules. From first law of thermodynamics, heat supplied minus heat rejected is equal to work output. This is cyclic integral of delta Q is equal to cyclic integral of delta W. Implies Q rejected from the cycle is 200 by 3, that is heat supplied, minus 50. This is 50 by 3 kilojoules. A is the answer for the problem. Now let us consider another problem, a conventional problem of 5 marks given in GATE 2002. Air at 327 degrees centigrade and 400 kilopascal with a volume flow rate of 5 meter cube per second flows through a turbine and exits at 100 kilopascal and 182 degrees Celsius. If the expansion process is polytropic, calculate power output rate of heat transfer and rate of change of entropy. Take Cp of air as 1.0035 kilojoule per kg Kelvin, gas constant of air, that is small r value, as 0.287 kilojoules per kg Kelvin. The solution to this problem could be given as like this. Let us represent the problem pictorially. It is a gas turbine working on air, which is ideal gas. He has given temperature as 327 plus 273, inlet temperature as 600 Kelvin, inlet pressure as 400 kilopascal, and exit pressure P2 as 100 kilopascal, that is equal to the atmospheric pressure, and T2 is equal to 182 plus 273 Kelvin. The volume flow rate is equal to 5 meter cube per second. This is corresponding to the inlet pressure P1 and the temperature T1. Here the system is open and the process is reversible polytropic, which may be indicated as PV to the power of n is equal to constant. Now the problem is the value of n. The value of n is how much? Let us first calculate the value of the polytropic index n. I use the polytropic relation between initial and final states. Because both the pressures were given and both the inlet and exit temperatures were given, I use polytropic relation P2 by P1 whole to the power of gamma minus 1 by n minus 1 by n is equal to T2 by T1. That T2 is equal to 182 plus 273 divided by 600 Kelvin. Any temperature ratios must be in Kelvin scale. Implies 100 divided by 400 to the power of n minus 1 by n is equal to 182 plus 273 by 600, from which the value of n could be calculated by taking the logarithms on both sides. We can take the logarithms on both sides and calculate the value of n, which may be obtained something like 1.25 or 1.3, because usually the value of n falls between 1 and gamma value. Gamma of air is 1.4, therefore the n value would fall between 1 and 1.4. That may be 1.25 or 1.3. Now coming to the work done per kg, the steady flow work or reversible work done by an open system is given as minus integral VdP, which is obtained after integration as n by n minus 1 into P1 V1 minus P2 V2, which can be taken as n by n minus 1 into P1 V1 into 1 minus T2 by T1. Because air is an ideal gas, P2 V2 by P1 V1 is equal to T2 by T1. Here the volume flow rate is given, therefore the power output is equal to work done per second is equal to inlet pressure is given as 400 kilopascal and inlet volume flow rate is given as 5 meter cube per second into n by n minus 1 into 1 minus T2 is 182 plus 273 divided by 600 Kelvin. So this gives the work done per second in kilojoule per second or kilowatts. This is one of the answers asked. And to calculate rate of heat transfer, we can use steady flow energy equation, that is Q minus W is equal to delta H. Because air is an ideal gas, the change in enthalpy of an ideal gas in any process can be taken as Cp delta T, that is Cp into T2 minus T1. Therefore rate of heat transfer is equal to rate of work done, that is power output, plus Cp of the air into 182 minus 327. Cp of the air is given, rate of work done is calculated above, and rate of heat transfer could be calculated in kilojoule per second. There is a small correction here. Here in this problem, left hand side rate of heat transfer in kilojoule per second, rate of work done is also in kilojoule per second. Therefore, the mass flow rate must be multiplied with the change in enthalpy per kg. How do we obtain the mass flow rate here? Mass flow rate of air could be obtained as I use the ideal gas equation P1 V1 divided by RT1, where P1 is given as 400 kilopascal, volume flow rate is 5 meter cube per second, R value is 0.287, inlet temperature is 600 Kelvin. This gives the mass flow rate in kg per second. This mass flow rate could be substituted here and the rate of heat transfer can be obtained. When you are using the steady flow energy equation, we have to take extra care whether all the quantities should be in kilojoule per kg or joule per kg, or all the quantities should be in joule per second or watts. To calculate change of entropy per second in the above problem, we can use the change of entropy relation, that is delta S is equal to Cp log T2 by T1 minus R log P2 by P1. So many kilojoule per kg Kelvin. Multiplying both sides with the mass flow rate into delta S, that is rate of entropy change in kilojoule per second is equal to mass flow rate of the air into Cp of air is given as 1.0035 logarithm of natural logarithm of 182 plus 273, that is T2 divided by 600 minus 0.287 into natural logarithm of 100 kilopascal divided by 400 kilopascal. Ln means natural logarithm, that is base E. So from which the rate of entropy production could be calculated by substituting the mass flow rate of air, which was calculated earlier. So the resultant answer will be rate of entropy generated. Rate of entropy change in kilojoule per Kelvin. Now let us consider another objective question given in GATE 2005. A vapor absorption refrigeration system is a heat pump with 3 thermal reservoirs as shown in a figure. The refrigeration effect of 100 watts is required at 250 Kelvin when the heat source available is at 400 K. Heat rejection occurs at 300 K. The minimum value of heat required in watts is, first let us consider the problem given along the figure given along with the problem. The figure along with the problem is given as there is a vapor absorption refrigeration cycle exchanging heat with 3 reservoirs. It is supplied heat from the 400 Kelvin and absorbing heat from 250 Kelvin of how much? 100 watts, which has been given in the problem, and rejecting heat to the 300 K reservoir. The answers given as A 167, B 100, C 80, D 20. If you look at the problem, the vapor absorption cycle is exchanging heat with 3 reservoirs. It is being supplied with heat supply. It is supplied with heat from the 400 Kelvin reservoir, and the cycle is absorbing heat of 100 watts from the 250 Kelvin reservoir and rejecting heat to a reservoir at 300 K. For minimum heat supply, from the 400 K reservoir, that is an external effect required to drive the machine, the COP of cycle should be maximum. When is the COP maximum? The COP is maximum only when the cycle is reversible cycle or refrigerator must be working on reversed Carnot cycle. So the cycle must be reversible. Applying Clausius inequality, to the cycle, that is, which states that cyclic integral of delta Q by T is 0 for reversible cycle, implies plus Q supplied from the 400 Kelvin reservoir divided by 400 K plus 100 watts of heat taken from the 250 Kelvin reservoir minus Q rejection divided by 300 K reservoir, 300 Kelvin temperature should be equal to 0. This is the Clausius inequality applied to the system. This is also called as second law of thermodynamics applied to the cycle. Now coming to the first law of thermodynamics, cyclic integral of delta Q is equal to cyclic integral of delta W implies 100 plus Q supply is equal to Q rejected. So, substituting first law in the above equation, we get Qs divided by 400 plus 100 divided by 250 minus 100 plus Q supply divided by 300 is equal to 0. There is only one equation with one unknown, hence the heat supplied could be calculated in watts. This is the answer to the problem. Here the assumption is the cycle should be reversible because he has specifically mentioned in the problem that minimum amount of heat required. Minimum means COP should be maximum. For COP to be maximum, the cycle must be reversible or Carnot. Now we shall discuss about very important diagram, that is Mollier chart, that is H versus S diagram for steam. Let us see how do the Mollier chart appear and what are the various important lines. It is the H versus S curve in kilojoule. S is kilojoule per kg Kelvin and enthalpy is in kilojoule per kg. It does have a dry saturated vapor line dividing two domains, namely wet region of the steam where dryness fraction is less than 1 and dry saturated vapor line has got x is equal to 1, and above the dry saturated vapor line it is superheated region. It has many constant pressure lines indicated as the rightwards sloping lines. The constant pressure lines are straight lines till the dry saturated vapor line. Above that they become curves. In the wet region they are straight lines, whereas various dryness fraction lines could be seen as x is 0.9, here x is 0.8. These are all the curves given as various dryness fraction lines. The constant temperature lines will go horizontally initially and later they merge with the constant pressure lines. That means in the wet region isobaric is nothing but isothermal. That is important point to be noted here. In the wet region, that is in the region below dry saturated vapor line where x is less than 1, isobaric line is nothing but isothermal line, because for a given saturation pressure there is only one fixed value of respective saturation temperature while the change of phase is taking place. Now let us consider an objective question. A certain amount of fluid at T1 is mixed with an equal amount of the same fluid at T2 in an insulated container. Considering the total fluid as the system, in the process of mixing A, the energy of the system is conserved. B, the entropy of the system increases. C, the entropy of the system decreases. D, the entropy of the system is conserved. In this problem, considering the container as the system, the solution is given as: consider the container as the system, which is obviously closed system. Writing first law of thermodynamics, Q minus W is equal to delta U. In this case it is insulated, Q is 0. There is no work done, implies change in internal energy is 0. Energy of system is conserved. That is half of the answer. But what about the entropy? Since the process is irreversible. Why it is irreversible? It is heat transfer through finite temperature difference. Since the process is irreversible, there must be increase of entropy because the system is adiabatic. Whenever an adiabatic system undergoes, here the important note to be remembered is, whenever an adiabatic system undergoes an irreversible process, the entropy of the system should have to increase. Therefore, the answer is the energy of the system is conserved, A, and the entropy of the system increases. Both A and B are the answers. Now consider another problem regarding the steam. Superheated steam at 3 megapascal and 300 degrees centigrade enters an adiabatic turbine and leaves as dry saturated steam at 50 kilopascal. Calculate the power output of the turbine if the steam flow rate through it is 1 kg per second. Solution. Here writing SFEE, steady flow energy equation, or first law of thermodynamics applied to open system in any process, whether irreversible or reversible, Q minus W is equal to delta H. Here, because turbine is adiabatic, Q is 0. Multiplying both sides with mass flow rate of the steam is equal to m dot into H2 minus H1. If enthalpy is in kilojoule per kg, the product of m dot into delta H is in kilojoule per second. Where in this here in this case it is kilojoule per kg. Mass flow rate of the steam is in kg per second. Therefore, multiplying with minus on both sides, we get power output is equal to mass flow rate of the steam into H1 minus H2. Here H1, that is inlet enthalpy at 30 bar, 3 megapascal means 30 bar, and the superheat temperature of 300 degrees centigrade is given as 2993.5 kilojoule per kg. This is obtained from the tables. And H2, that is HF, F for dry saturated, Hg for dry saturated vapor enthalpy at 50 kilopascal is given as 2646 kilojoule per kg. Therefore, power is 347.6 kilowatts. This is the answer.